Is it okay to stand here? This is fine.
Preferable advice is that you stay near the podium, but if you want to move a bit, you can move. But the only problem is that sometimes, I mean, just don't go too far.
Yes. Okay. I think I'll be pretty much between
You
you.
will start back.
I see.
That's what generally I have noticed.
Okay.
That's why I ask people to stay there on the podium so that they can, take the reference of the slides from there, or maybe from the desk, so that their face is visible to the people who is watching.
Okay.
Okay, so Shibashis is a faculty member at the School of Technology and Computer Science at the Tata Institute of Fundamental Research. He has worked on a variety of formal methods topics with a strong focus on reactive synthesis. He got his PhD in IIT Delhi, then did a postdoc at the University of Jerusalem, and then at the ULB in Brussels, where I had the pleasure of collaborating with him. Today, we'll talk about stochastic window mean-payoff games. So you have the floor.
Thank you, Damia, for the very kind introduction. So am I audible? Okay, thanks. So I'm going to talk about payoff games. So this is a joint work with Laura Doya and Prangshu Gaba, who also happens to be the next speaker. And I also should thank Prangshu because some of the slides I actually took from him to start with. So let's begin. So to start with, what are stochastic games? So essentially, here we are talking about two players. So we have a controller, player one, and we have a player two, which is an environment. And this environment is antagonistic or adversarial environment. And we are also talking about zero-sum games here. And these are turn-based games. And we will also see that there are some probabilistic nodes in this game. So these are going to be like, we call them games on graphs. And we would assume that in the graph, there are no deadlocks. So it will be clear in a while. What do we mean by that there are no deadlocks? So essentially, it means that whenever you reach a particular state or a particular vertex in the graph, you can always choose some action from that vertex. So that's what I mean by no deadlock. So here, this is an example of a graph. And I mean, a stochastic game. So the underlying graph you can see. So there are some circles, there are some diamonds, and there are some squares. So the circles are the player one or the controller vertices. So there are these three kinds of vertices, and the squares represent the environment, and the diamonds are the probabilistic vertices. So from where you have probabilistic choices. So it will become clear in a while what we are talking about. So yeah. So we now say how the game is played on this for the stochastic games. So you start with a token on some vertex. So let's say we have a token on a vertex v0, and like there may be several choices, right? So we have two choices, and since this vertex v0 is controlled by player one, it's player one's sort of choice to go to the next or the successor vertex. So here, for example, player one can choose to go to v1, and then from v1, again, it's a probabilistic vertex. So depending on the underlying probability distribution, you can go to one of the successors. So let's say you go to v2, and again, v2 is a player one vertex. So player one chooses to go to its successor. Here you have only one possible option. So player one goes to v3, and from v3, player two. So player two, the adversarial player, again has two possibilities. So the adversarial player chooses to go back to v2. right? So this is how a particular play, this particular play progresses, and so on, right? So this is an example of a play. And now what we are going to study here in this talk, we are going to talk about window mean payoff objectives, right? So before I talk about window mean payoff objectives, let's also look at, for example, like here we have also on the edges some payoffs. So these are quantitative games. So whenever there is a play, there is a payoff which is also associated with the play. And each edge E here has a rational play payoff, and every time the edge E is traversed, player 1 receives this payment of W, the weight on this particular edge, from the other player. Okay, so let's say you have this particular play starting from V0, V1, V2, and so on, and the corresponding payoffs, as you can see, are the sequence of these integers, or we were talking about more generally rational payoffs. And now, one question that we could ask very naturally, how do we measure how good a play is? So we are given a play, there are some associated, like on every edge, you get a payoff, and we are trying to talk about how good a particular play is. Now, there are several such measures. So one very common, one popular measure of the goodness of a play is in terms of mean payoff. So you have, for example, like you look at a play of some particular length n, and then the mean payoff is like you sum over all the n edges, and then you divide it by n, right? So this is a mean over this finite play. So this is what we are talking about. So you have -2, -3, -1. The mean is here -2, and so on. So this is how you are computing. And then the mean payoff of a given play pi. So here we are talking about an infinite play pi. This is as n tends to infinity. In general, a limit may not exist, but it's like the lim sup over n and 1 over n over all these finite path. As n tends to infinity, we are choosing the lim sup. And this is what we call the mean payoff of this play pi. Okay. Now, we can say, for example, a play pi is good for player 1 if the mean payoff of this play is non-negative. Now, there are certain characteristics of a play, and we are talking about characteristics of a good play, which is good in terms of the mean payoff, is that it can have arbitrarily long windows or long infixes over which the play may not really be good. So, for example, if you look at this particular play here, right? So you have -1, +1, then 2, -1, then 2 + 1, then again 2 - 1, 2 + 1, and so on. So, well, the mean payoff of this play is going to be 0. On the other hand, if you see that there can be arbitrarily long windows, arbitrarily long infixes of the play, where this can go like lower than 0. It can be -1. Okay, so this is not a good behavior. So this is what I mean. What we are trying to say is that, for example, like if I'm trying to get some returns, for example, right? Like I'm talking about some returns over some period of time, it's not a good idea to sort of go below the mean payoff for arbitrarily long, the expected, like what is the desired value, to go below that desired value for an arbitrary long period of time. So that's where this notion of window mean payoff kind of comes in. Okay, and now, so what is the notion of window mean payoff? So we look at a play and we are trying to see here when starting from a particular vertex, we kind of get a mean payoff of mean of 0. Okay, so it will be clear in a while. So here, for example, starting from V0, you get -2, then you get -5. It's still negative -6. It becomes -1, and so on. So now we see that the mean payoff the mean has become 0. Right? So we are just trying to look at like some windows over which we are getting to see that the mean payoff becomes non-negative for the first time. Okay, so that's the idea. And well, now you can again start from the next vertex. Okay, so the idea is that in that play, from every vertex, I would like to ensure that over some finite window, my mean payoff, it becomes non-negative. So you start from the next vertex, and again you see that it became like at this point, starting from V1, when you reach V4, it becomes, the mean becomes non-negative. Okay, and we call it that the window closes. Until the window closes, the window remains open. So this is the terminology I'll be using quite often, right? So whenever the mean becomes non-negative, I'll say the window has closed. The window that started from V1 has closed at V4. Okay, until V3 it remains open. Good. And similarly, we look at like this and so on. Okay, so it's clear from every vertex, I'm trying to see when the window closes, when I'm going to have a mean payoff which is getting non-negative for the first time. Right. So now I will define this particular objective, which is called the direct window mean payoff objective. And here I'll say that the window length is given. Okay, so the idea is that I'm given a window length, and I'll try to see that starting from a given vertex, if I can find a play such that in all vertices, starting from all vertices in that play, a window gets closed. Okay, and the window length is given. Okay, so over this L length, the window is getting closed. Sorry. Okay, so it means now if I see that a play does not satisfy the direct window objective with parameter L, the window length L objective, if the play contains an open window of length L, right? So I'm talking about like you starting from here at every vertex, at every position, a window should be closed within L steps. So if that objective is not satisfied, that means that there exists a position somewhere in that play where the window is not getting closed. Clear? Good. Now just to see that we are following this thing, let's look at a couple of examples. So if I look at this particular play V1, and then we are taking this loop V2, V3 for, infinitely. So in this case, we see that where my L is 3, so I want to close a window within 3 steps, in at most 3 steps. Now, starting from V0 itself, the window is not getting closed because you have -2, -2, -1. So you have -5, the window is not getting closed. Now, coming to this particular play, V0, V4, V5, and when you take a loop on the V5, you come to V6, and then you are in that loop over that V0, V4, right? So this one, we can see, for example, so which one is the sort of the crucial thing that we should look at is here. So when I'm at V5, I take a -1, V5, V5, and then can I close it? Yes. After that, I'm taking this, I'm going to V6, so I'm getting a positive payoff, and the window closes. So this thing is fine. And similarly, also we can look at this loop, which is also like if you look at that -2, starting from -2 in 3 steps, in fact, I am not able to close -2, 0, +1, it's still negative. And so it's not a good window, doesn't satisfy the direct payoff. Okay, so now I'm slightly changing the objective. So I'm saying that eventually in a play, I would like to close the window every time. So I'd like to start from some vertex. So there is my initial vertex. And now I'm talking about eventually I would like to go somewhere such that from that point on, it will be like a direct window objective, right? So this is something like a prefix independent objective, right? By prefix independent, what I mean is that this particular play does not really depend on the prefix, some initial prefix. If you change the prefix and if you keep the suffix sort of the same, then it's still going to, like this eventuality property, it's still going to hold true. Yeah. Now, in this case, just notice that a play does not satisfy this objective. Since it's a prefix independent objective, it will not satisfy this window mean payoff objective. Recall that we are no longer talking about the direct window objective, but we are talking about this window objective, which is like an eventuality property. Now, it will not satisfy if the play contains infinitely many open windows of length L. Right? If it happens there are only finitely many open windows, then after some point of time, you reach somewhere and then it will always be closed. Right? Then it's actually satisfying the window mean payoff property. So if this property, if the window mean payoff is not satisfied, since it's kind of like you are talking about this eventually this thing. So there should exist infinitely many open windows of length L. Okay, good enough. Now again, we can see which of these things. So if the now, okay, so here if you recall that earlier this direct window objective was not satisfied for this play, but now here we are in this cycle, right? This V2, V3, and this gives you like starting from V2, and if you in 2 steps you are having like a total payoff of 0 or the mean payoff of 0. So this window is getting closed. So eventually you are reaching V2 starting from V0 from where the window is getting closed, right? So this is sort of the difference, and I think I'll just skip the I think it's sort of easy to see these examples. Now, what is the problem that we are looking at? Okay, so any question with the definition so far? Is there any question? Okay, with the model, right. So now we are looking at this particular problem. So what are we saying? We are given a stochastic game, right? So we looked at the stochastic game. There were 3 kinds of vertices, and we are also given an initial vertex V, and we are also given a window length L, right? The window length L, which is greater than or equal to 1. And we are asking this question: if it begins starting from vertex V, does player P1, it's like we have heard about system environment, it's like the system player. So does player P1 satisfy the window mean payoff objective with positive probability? So that means, so we have these probabilities, right? We have these probability vertices. So we are asking, does it satisfy with positive probability or with probability 1? Or if I'm given also a threshold probability P, then does it also satisfy with probability at least P? So these are the 3 different questions that we are trying to solve here. Okay, right. And these games are determined. So this comes from determinacy of Martin. So Martin's determinacy theorem, which essentially says that these games are determined. So if, for example, if player 1 positively wins, then player 2, yeah, I mean, if either player 1 positively wins or player 2 almost surely wins the complement of the objective. Okay, or you can say that if player 1 wins with probability P1, then player 2 will win for the complementary objective with probability 1 minus P, and so on. Okay, so to start with, we'll talk about the positive and the almost sure winning objectives, right? So the basic framework is the following. So we have this stochastic game. So we were talking about this stochastic games. So we will reduce these stochastic games to non-stochastic games. So which means that these are 2-player games where there are no probability vertices. So you have only 2 kinds of vertices, player 1 and player 2, system and environment. There are no probability vertices. So we will reduce the stochastic games to non-stochastic games. And this window mean payoff objective, so this has already been studied for this 2-player, right, non-stochastic zero-sum games, and then we'll use the ideas there, the techniques there to solve the non-stochastic game. Okay, so again, so we are reducing the stochastic version to non-stochastic game, and then we are using we are solving the non-stochastic games. Okay, so this is a very broad idea, and I'll define something called a positive attractor. So you are given a target set of targets, like which is given by capital T set of vertices, and the idea is that so the positive attractor of this target set T is the set of all vertices from which player 1 can ensure with positive probability that the token will eventually reach this target set T. Okay, with positive probability, you will reach the target set T. This is what I am calling the positive attractor. And the way to compute this is very simple. Like suppose your target set is V2, and how do you compute this the set of vertices from which you can, where player 1 can ensure that you can reach V2 positive probability? So you look at, for example, the predecessors of V2. And so one is V1, then the other one is V3. So from V1 you can certainly reach, but from V3 it's a player 2 vertex, right? So V3 could have reached V5 instead of going to V2. So we would only include V1. And then once we have this set, then we look at the predecessors of the vertices which are in this set. So again, we have V0 and V1. Now, V0 being a player 1 vertex, player 1 can ensure that it reaches V1. So we will also add V0 to the attractor. Okay, so this is like an iterative algorithm, and it just continues, and we'll see that these green vertices are essentially the positive attractors. Okay, and the complement of a positive attractor is actually a trap. So a trap, essentially, it means that player 1 cannot go out, doesn't have a strategy to go out of this set of vertices, which are a trap. But anyway, so this is like slightly less important. And another thing that we are going to use, like as I was saying, the way we are going to solve the stochastic game is by reducing it to non-stochastic games. So what we will do in our notion of non-stochastic game, all the probabilistic vertices that were there, will change it to player 2 vertices. Okay, so this is so if you have this G, then by changing the probabilistic vertex to a player 2 vertex, we get this GNS. Okay, so these are just some notations, and now we will see how we solve the positive winning for. So essentially what we are trying to see, we are trying to find out the set of vertices from which player 1 can satisfy the WMP, the window mean-payoff objective, that is eventually you can get all the windows closed, that objective, given this window length L, with positive probability, with non-zero probability. Right, so we are trying to find out that region or the set of vertices from which player 1 can ensure this. So here is the algorithm, and then I'll give some ideas about it. So we are given as input the stochastic game G, and we construct the GNS, which is the non-stochastic version. And how do we construct the non-stochastic version? Recall that we changed all the diamond vertices, the probabilistic vertices, to player 2 vertices. And now we solve that game, we get the winning region, the player 1 winning region for this non-stochastic game. And now let's focus on this part. So now we are saying that let's look at the positive attractor of this winning region in the non-stochastic game, and that is certainly what we are saying is that is certainly winning, like positive winning. So if you have the positive attractor of this winning region, that is certainly positively winning for player 1 in the stochastic game. And now we look at the remaining part of the game. So essentially it's called a subgame. So we are removing this positive attractor, which I'm calling A1. I'm removing this set of vertices from the whole game, and whatever I have, I again call with this subgame the same routine. So I'm recursively calling the routine with the subgame. Okay, so let's see. So here is the idea. Now it may happen that at some point of time, if it happens that the winning region in the 2-player game for player 1, if that is empty. So what does it mean? That from all the vertices in the 2-player game, in the non-stochastic game, it is player 2 that wins. If it is the case that player 2 that wins, then we are also claiming that entire set of vertices is also winning for player 2 in the stochastic game. Okay, so this is what this part says, but let's continue. I think it will become further clearer. Right? So again, so here I'm saying that if this entire set of vertices is actually winning for player 2 in the non-stochastic game, then this entire set of vertices is also winning for player 2 here. So player 1 doesn't win from any of the vertices here positively for the WMP objective. Okay, so let's go ahead. I mean, I think it will be clearer if okay. So here, for example, like just as I was saying, that you have the total game and you play the you play your in the non-stochastic version of the game, you play, and let's say the W1 is the winning region for player 1 in the non-stochastic version. We compute the positive attractor, we remove it, and now we play in this subgame, and again we compute the W1, you have the attractor, you remove it, and this continues. And maybe at some point of time you will see that it may be possible that now there doesn't exist any vertex in the remaining in that subgame from which player 1 is winning. Okay, and this is in the non-stochastic game. And if player 1 doesn't win from any of the vertices, our claim is that player 1 also doesn't win from any of the vertices in the stochastic game positively. Okay, so from all these vertices, player 2 almost surely wins. Okay, any question on the terminating condition? Yes.
Yes. Just to make sure I understand this well, so in GNS you make the probabilities adversarial,
Yes.
right?
Yeah.
Like they belong to. But so then the guarantee that I get as controller is that if I can win this, then I have probability 1 of winning.
It means that in the non-stochastic game, it's the case that from every vertex, player 2 is winning. Okay, in the non-stochastic game, player 2 is winning.
So maybe it's because of probabilities, or maybe it's because of the adversary, one or the other.
Yeah, it's maybe in the non-stochastic game, player 2 is winning, and in the non-stochastic game, we converted the probabilistic vertex into player 2 vertices. Now I'm saying, now if you go back to the original game, right, and if it is the case that in the non-stochastic game, all the vertices are winning for player 2, then it's indeed the case that in the original stochastic game, also player 2 wins from all the vertices.
Okay.
Almost surely.
Okay.
Wins almost surely. So that means that player 1 doesn't win positively from any of the vertices. Okay, so that's the claim, and that requires, of course, a proof. But I will not go in the details of the proof. I'll try to give some. This is an important kind of a lemma, but I'll try to give some intuition of this, how we do this. Okay, so I'll just skip this example. Maybe, I mean, it's kind of like we looked at this. Right. Now, this is what I was saying, that if player 1 does not win from any of the vertices in the non-stochastic game, then player 1 also does not win positively from the original game, in the stochastic game, for this WMP objective. Okay, so in the other way to state is that if player 2 wins from all the vertices in the non-stochastic game, then player 2 almost surely wins from all the vertices in the stochastic game. Okay, so these are just equivalent statements. So the thing is, like, so if player 2 wins, so let's look at the alternative, the idea with this alternative formulation. So the idea is that suppose player 2 wins from all the vertices in the non-stochastic game. So that means player 2 has a winning strategy. Let's call it sigma 2. And then we can construct another strategy sigma 2 prime that is almost sure winning in the stochastic game from all the vertices. Clear enough? And what I would like to emphasize that given any strategy sigma 2, which is winning in the non-stochastic game, that same strategy sigma 2 may not be winning in the original stochastic game. So we would like to construct some strategy sigma 2 prime from sigma 2, and we'll see how this works. Okay. So we have, let's say the idea is that, like, we have this, we'll see whole kind of like in a stochastic game, a play deviates from a play that you would have in a non-stochastic game. Okay, so for example, it can happen that when you are in V1, when you are in vertex V1, right, in the non-stochastic game, recall that this V1 will be converted to a player 2 vertex. And now here the strategy of player 2 may be to reach from V1 to V2, correct? But now when I'm talking about the stochastic game, it may happen that I indeed, because this is a probabilistic vertex, with some probability I can indeed come to V3, right? But this way that coming from V1 to V3, you would not see in the non-stochastic game, right? So this is what we would call a deviation. Okay, the idea is that whenever there is a deviation, we would detect the deviation and we would reset sort of the play. Okay, so by resetting, I mean that whenever you see a deviation, so you have come to V3, and then we'll say what was my original strategy when I see V3 in the beginning of a play. So I'll change my strategy sort of to take care of this deviation. So let's see. For example, so in fact, a deviation may cause player 2 to lose. So as I was saying, that it may happen that the play would not from V1, it would not come to V3 when I'm talking about the non-stochastic game. But when I'm talking about the stochastic game, then it may come here. Now, considering the non-stochastic game, when you are going to V2, like considering such a finite strategy, like you are starting from V0, then going to V1, then V2, okay, and you may sort of come along this particular, like you from V2, the strategy may be something like that, you come to V3, then V5 and so on, okay? But it may happen that when you are coming from V1 to V3, for such a finite prefix, player 2 had a strategy that you loop here, okay? Which actually, such a play you wouldn't see in the original non-stochastic, in the non-stochastic game. But when you have the stochastic game, such a thing can happen. So let's just look at this. So maybe like what I'm saying is that when you see V1, you go to V2, and then like what we are saying is that from V2 in the non-stochastic game, you come to V3, and from V3 you would go to V5, okay? And here you see V5, and from V5 you loop, right? And once you loop, you are always seeing -1. So this is the strategy in the non-stochastic game. So again, like you are going from V0 to V1, V1 to V2, V2 to V3, and V3 to V5, and then loop. So this is, I'm talking about the strategy in the non-stochastic game. And this is winning for player 2 because you are looping here and you are getting a payoff of -1. This is winning for player 2. But now, suppose in the case of the stochastic game, it can happen that when you see V1, you may reach V3, right? Because with some probability you may reach V3. And the strategy may say, the previous strategy may say that if you come, if this is the prefix, so after V1 if you reach V3, after V1 here, see, you after V1 if you reach V3, then you go to V2. Okay, this is what this strategy says. After, when you see V3, you go to V2. And then from V2, again, you come to V3, right? This is the only possible option. So you are in this loop. If you come along this path, then you will be in this loop. So this is what the strategy says. But the thing is that this was never happening. This path were never happening in the non-stochastic game. Okay. Now, so whenever you are here, now you see that there has been a deviation. And now you will see that, oh, what happens if I had seen V3 in the beginning? Now this says that if I had seen V3 in the beginning, I would actually go to V5. So I will change sort of my strategy. I'll say my sigma 2 prime will be like this, that whenever I'm seeing V3, I'll go to V5. So the basic idea, again, the overall idea is that I should be able to detect a deviation, and whenever there is a deviation, I'll reset my strategy, and following this reset strategy, this is it will be, this reset strategy is almost surely winning. Okay, so this is the idea. Okay, so I think about the algorithm for the positive winning, right? And now we will look at how do we solve the almost sure winning. So any question before we proceed to this almost sure winning? Okay, right.
Just to make sure, so this idea that you need to adapt to deviations is because your strategy is not memoryless, right? You need your strategies to not be memoryless. Like
memoryless. So I didn't talk about the memory so far, but what happens from these algorithms? Like if you look at, so the memory that is recovered is essentially the same as the memory that is recovered in the the non-stochastic two-player game. The remaining part is all about like attractor computation, and this is what we are doing. Like you have the subgame, and there you were talking about the attractor, and then you were also talking about in the subgame you are solving the non-stochastic two-player game.
Yeah, but
right?
The attractors are memoryless.
That's the strategy coming from solving the non-stochastic two-player game. So the memory that is recovered for the positive winning, as we saw, is the same as the memory that is recovered for the non-stochastic two-player game. Okay, thanks. So now we'll look at the almost sure winning. So what is almost sure winning? So we want to find out the region or the set of vertices from which player 1 can ensure that this objective is satisfied, right? The window mean-payoff objective is satisfied with probability 1. Earlier we were talking about positive winning, which is that with non-zero probability. Now we are talking about a stronger thing that I want to satisfy this objective with probability 1. And how do we do this? So we are saying again, here we are using the positive winning algorithm that we just saw. So so first we compute the set of vertices which are positive winning just by calling the previous routine. Okay, so these are the set of vertices from which player 1 wins positively. And now I'm just removing this from the entire set of vertices V. So this gives the set of vertices from which player 1 does not positively win. That is what my W2 is. Player 1 does not positively win. Correct? So this means that this W2 is the set of vertices from which player 2 almost surely wins. Player 2 wins with probability 1. Okay? Now let's skip this if part and come to the else part. The else part says now I have this W2 where player 2 is winning almost surely with probability 1, and I look at the positive attractor of player 2 to that W2. Positive attractor of player 2 to that W2. So you have W2 and you consider an A2 around that W2 from you can win positively. So then from A2, player 1 cannot win almost surely, right? Because player 2 is winning positively from the whole of A2. Player 2 is winning positively from the whole of A2. So that's why from any vertex in A2, player 1 cannot win with probability 1 because player 2 is winning with non-zero probability. Okay, it's clear, right? So now we are going to remove that set A2 then because there is no hope for player 1 from A2. You remove that. Now you look at the subgame and then you kind of again recursively compute this thing. Okay, so and here also there is a terminating condition as we saw earlier, which says that if W2 equal to 5, so that means that my entire set of vertices it is winning, right? W2 equal to 5 means V equal to pos win. So entire set of vertices is positive winning for player 1. And here there is a nice, again, nice statement by Krishnendu and it's by Krishnendu only from 2007. So which says that for any prefix independent objective, if you have that all the set of vertices in a game, in a stochastic game, if all of them are positive winning, then all of them are also almost sure winning. Right? Is it clear? So this gives if W2 is empty. So again, if W2 is empty, that means that all the vertices are positive winning, V equal to pos win of G. And the statement and the theorem states, which we'll see, is that if all vertices in a stochastic game are positive winning, then all the vertices are also almost surely winning. Okay, so this is the terminating condition. Okay, so again, so we compute the W2, and then we are saying that you have the positive attractor. No hope from the positive attractor because we are talking about almost sure winning for player 1, and this is positive attractor for player 2. So we will just remove that part, look at the subgame, and this continues. This continues, and somewhere it may be the case that the W2 is empty, which means that player 1 wins positively from everywhere. And I'm saying that if player 1 wins positively from everywhere, that is equivalent to saying player 1 wins almost surely from everywhere. Okay, so this is again not very difficult, but it of course requires a proof. I'm not getting into that, and just okay. So this is, so it says that player 1 positively, if player 1 positively wins WMPL, actually the result is more general. It actually holds for all concurrent prefix independent objectives. I didn't talk about concurrent games, but essentially it also holds for turn-based games, right? If this is the case, then from everywhere player 1 is positively winning, then player 1 also almost surely wins from everywhere. I mean, to think of this, like you can think of something like a Kobushi objective, like you think of like from everywhere I have a way to positively win in a finite game. You can say that you can like almost surely will go and get stuck there, like in the Kobushi set. Okay, right. So now the winning region. So okay, so now we are trying to talk about how much time do I have? 10 minutes or so, right? Yeah. Okay, thanks. Okay, so now this result from Chatterjee and Laura Daya, Mikhail Rando, and I think Jean-François Rasca. So yeah, so this paper, so this is a journal version which actually solved the two-player window mean-payoff game, and there they show that when L, the window length, is given in unary, then you can solve the two-player non-stochastic game in polynomial time. Okay, there is some sort of motivation behind considering the window length to be given in unary, because it's assumed that the window length is much smaller than the entire state space. It's kind of a standard assumption, so the window length is sort of it's assumed to be unary, and this two-player version, the non-stochastic two-player version, can be solved in polynomial time. And for the positive winning, we have like an order V. Like you recall that we were having these subgames, and every time we were removing some vertex, right? So it's like order V times C, where C is that complicated looking equation, V times C expression. And for the almost sure, if you recall, the almost sure was calling the positive routine. So I have another V there, another V times, like we were also constructing subgames there. So it's V squared times this complexity, right? So what we have is the positive and almost sure decision problems for window mean-payoff L, where L is given, and we are saying that it's given in unary. This is in P time. And the memory required, coming to Damia's question, the memory required by both the players is more greater than that in the non-stochastic games, because all we are doing is some abstractor computation, and then we are solving the non-stochastic, the two-player zero-sum non-stochastic game, right? So the memory required by both the players is the same. And now coming to the value problem. So what is the value problem? So the value problem was you were also given a probability threshold P, and we are asking the question, can player 1 ensure that this window mean-payoff objective is satisfied with this probability P? Okay, so this is the value problem. I mean, you can also look at it a bit more formally as like supremum over all the strategies of player 1, infimum over all the strategies of player 2, and then this objective. Okay, is that greater than equal to P, right? This probability P. Now, what it says, so there's a paper by Krishnendu and Tom and Florian Horn, which says that if phi is a prefix independent objective and A is some oracle. So today morning we were talking about, we were listening to this talk where we looked at these Turing machines with oracle calls, right? And so I'm saying that it may not be necessarily an NP oracle. You just consider some oracle A. If A is an oracle for the positive and the almost sure decision problem, then this value problem can be solved by a non-deterministic polynomial time Turing machine with this oracle access to A. Okay, so so the positive and the almost sure decision problem we could see for this WMPL objective. So this is a very general statement for any prefix independent objective, right? Then for the window mean-payoff objective, the positive and the almost sure decision problems, we saw that this can be solved in polynomial time. right? So for this, for the value problem, for window Mean-Payoff objective can be solved with NP, using an NP machine with a P oracle, so which is the same as NP. And it's not again very difficult to see that this problem, like what that statement says, this value problem for this arbitrary prefix independent objective phi, it's also in NP with an oracle access A. So what we have is that the window Mean-Payoff objective, the value problem is in NP intersection co-NP. Okay. Good. So another objective I'll slightly briefly mention. It's called the bounded window Mean-Payoff objective. So what was the fixed window Mean-Payoff objective? We said that there an L was given, or the window length was given. In the case of bounded window Mean-Payoff objective, we are asking the question, does there exist a window length L? Does there exist some window length L such that from some point on, with that window length L, the windows will always get closed. Okay, does there exist such a window length L? Right. So essentially the play satisfies the BWMP objective if it satisfies the WMP L for some L greater than equal to 1. And so these are like equivalent statements, different ways of looking at them. So the BWMP objective is the union over all L WMP L, right? Okay, if there exists an L such that eventually all windows close in at most L steps. And now, if you look at the objective of player 2, that is a complement objective, right? It says that player 2 should win. So whatever be the window length you choose, window length 1, window length 2, window length 3, etc., player 2 should be able to win for all such window lengths. So that means that no matter what window length you choose, player 2 should be able to, the objective is that whether player 2 has the strategy that the window will remain open. Okay, whatever be the length of the window, right? So it's irrespective, I mean, whether it's window length 1, 2, 3, etc. So this is like the BWMP objective for player 2, the complement objective is the intersection of the WMP objective for over all L. Right. And so unlike the FWMP, unlike the window Mean-Payoff, the WMP objective where L was fixed, where we saw that the positive and the almost sure decision problems were in polynomial time in P. For BWMP, they are already, the positive and the almost sure decision problems are already in NP intersection co-NP. Okay, and again, just like the previous case for the WMP, for bounded window also, the memory required by both the players is no greater than that in the non-stochastic games. And for the value problem, you recall that very general theorem which said that for any prefix independent objectives, if the complexity of the positive and the almost sure are in A, then the value problem is in NP with an oracle access to A. And what one can show is that NP with an NP intersection co-NP oracle is the same as NP, and similarly co-NP with an NP intersection co-NP is the same as co-NP. Hence, the value problem for BWMP is also in NP intersection co-NP, right? So for BWMP, everything, positive, almost sure, value, all are in NP intersection co-NP. For recall that for the window Mean-Payoff of the previous one where the L was given, there the positive and the almost sure were in time, whereas the value problem was in NP intersection co-NP, right? So coming to conclude, so about what did we see? Here is what I just mentioned, that the WMPL objective, right, where the L is given or fixed, the positive almost sure are in P time, the value problem is in NP intersection co-NP, and this is kind of like similar to simple stochastic games, Mean-Payoff games, parity games, etc. I mean, it's very difficult to improve this thing because one can have an easy reduction from simple stochastic game to this WMPL objective, like so. And the exact complexity of simple stochastic games, I mean, it's known to be in NP intersection co-NP, but it's one of those rare combinatorial problems for which no polynomial time algorithm is known to exist. And for the BWMP objective, we found that everything is in NP intersection co-NP, positive, almost sure, and value problems. So future direction, the next talk, Pranshu is going to talk about the expected window mean payoff objective. Here I talked about something like that with this much probability, I would like to satisfy the window mean payoff objective, right? But now I can ask the question like, well, maybe with probability 0.3, I have a window mean payoff value of, let's say, 10. With probability 0.7, I have a value of -2, right? So what is the expected value there? Something like that. And so this is another interesting problem. So one can think of like, okay, you are investing in some mutual fund or some stocks, and then you would like to have a good expected return, right? Rather than being always safe from, let's say, taking risk, like not always being very risk averse, but you want a good expected return. And then one can also ask the question, can I find a strategy which will solve both the satisfaction and the expectation at the same time? So I want to be risk averse as well as I want to have a good expected return, right? So can you come up with a single strategy which will satisfy both the things together, right? So these are the kind of things we would like to look at or have been looking at. So yeah, so some of the papers, and then I think that's all. Okay, so thanks for your attention.
Thanks, Shibashis, for the presentation. So do we have questions? Yeah.
So is there any relation between, I mean, very much looks like games and energy games, stochastic energy games?
So I guess the complexities will be similar, but energy games are not really here. We were mainly focusing on objectives which are prefix independent, but energy games are not prefix independent, right? So many of the things that you see here, the techniques that we are talking about, the lemmas or many things we are using, they are very much dependent on the prefix independence of the objective, which may not be the case for.
Yes, like if the existing initial energy, like in
That's a good question, but again, like as I said, like even then also it's not a prefix independent objective, but yeah. But I think, okay, I don't know exactly whether they have been studied for stochastic, but yeah. And here also the other thing we are talking about this finitary objectives. It's like not, so finitary means there are this window there, right? So for a finite length, we would like to satisfy.
or like bounded, you don't
Bounded, like I'm trying to get a bound on the window length.
know if it has been studied for more than time-based, like
No,
there's a
don't think
subclass of concurrence.
I don't think so, because when we started looking at the literature, we didn't find any, particularly for, I'm talking about this window mean payoff. Of course, like there are papers, I said this particular thing about where if from all vertices, player one is positive winning, then from all vertices, player one is also almost sure winning. This holds for general concurrent stochastic games. I think this paper is called Concurrent Games with Tail Objectives or something like that. But yeah, window mean payoff, I don't think there is a concurrent version. The definitions are possibly not there, even for two-player kind of a thing where you remove.
But it's in subclass of not and beyond time-based, but
Yeah, that's what I'm saying.
Okay.
When you remove the non-stochasticity, it's a stochasticity when you have non-stochastic version. Yeah,
thank you.
don't
It was a nice talk.
study it.
Other question? So, in what you were saying, I have the feeling that the prefix independence was very useful.
Yes.
What could happen without? Like, does everything break, or is there some part of it that will work? Like, look at the direct movement layer. Direct.
Yes. So I think if you look at the direct variant, the one which I started with, so even for MDPs also, I believe that if you don't have the prefix independence, then the problem will become much more complex. Like you have to actually remember paths of length L and then look at things. Because without the prefix independence in MDPs, you know that there are these end components, so you can just analyze, focus on the end components, and there are some nice behaviors which happens already for MDPs inside the end components. But without this prefix independence, those things will be lost, and the complexity will be higher. Yeah.
My second question is a bit because I get. So if I was very stubborn and I didn't want the window
Sorry,
length,
if I was very stubborn, okay.
and I don't accept that the window length is in unary.
Huh.
It's in binary. Do I just need to say pseudo polynomial whenever you say pseudo
I-
polynomial, or is there something else that changes?
I guess like it will be pseudo polynomial, if you can say. Yeah.
So then, like the oracle arguments, I'm not sure what to do.
Sorry.
So then, when you had these oracles, right?
Huh.
I'm not sure what would happen then. I guess it, or it just, well, yeah.
Yeah, then it will be like an NP with this kind of a pseudo polynomial oracle.
There are no other questions. I mean, the short talk session that starts, I guess now.
Thank you.